do parametric equations. So this is chapter 9 stuff. And Calc 3 really starts in chapter 10. So parametric equations really are, we're looking at particle movement. So rectilinear motion. Remember doing that? So that can be defined parametrically. What we did is we drew the curve in terms of t above the s of t axis. The s, we kind of did like a three-dimensional look to a back and forth particle motion. That's a we're going to let that particle move in a plane, okay? P-L-A-N-E, not P-L-A-I-N. So it has a position, so the position of the particle is at over x up y at time t. Now we don't always have to let t be time. T doesn't have to be time all the time, but it could also mean like theta. So it could be an angle. There's a lot of different applications to this. Time is just a function of time, right? And the y position, I don't know where my y went. Y equals g of t. Did you see that?
No.
Oh, well, all right. Anyway, so t doesn't have to always be time. It could be like theta or something of that. That's part of the domain. So the domain of f or domain of x and the domain of y. So there's going to be t's that are in common. So where the t is part of both domains, then we're going to have the curve is going to be called the plane curve C. Okay, and so we're going to be looking at the plane curve C. And I think the best way to kind of go through this, as far as I'm concerned, on a short, abbreviated week schedule, not strong schedule, getting a lot done in a limited amount of time, is seeing some things with example. We're going to come up with the graph of these things. So what we can do is, let's just look at some examples. I'm going to go along, if you don't mind. I just kind of I could talk through the ones in the book, or I could try and do some others, but I think to kind of help you, depending on how much you've read through this, I know Luke read through it because he was doing it when Isaac was finishing his test up. But anyway, if we have parametric equations, x equals 2t minus 3 and y equals 4t minus 1. This would be a couple of them here. Basically, every t works, right? T could be negative. Now, if t is time, then t would be greater than or equal to 0, right? Yep. So, but anyway, in this case, if we want to sketch the curve, what we do is solve for one in terms of one of the variables. So I could solve this for t, and so 2t equals x plus 3. Man, this is horrible. 2t equals x plus 3, and then t equals x plus 3 all divided by 2, or 1/2 x plus 3/2, right? Then right there, I'm going to get that y equals 4 times the quantity 1/2 x plus 1/2 x plus 3/2, and then minus 1, right? Simplifying that, multiplying the 4 through there would be 2x plus 6 minus 1, and plus 6 minus 1 is plus 5, right? So 2x plus 5 equals y, and of course, what's that graph look like? That's a line, right? So if I graph that line, if I let x be 0, y equals 5, right? If I let y be 0, x equals -2.5 or -5/2. And there's no values that don't work here, right? So that's the parametric equation that's the plane curve there. So it's a straight line. All lines are straight, but the curve is a plane curve is a line. Does that make sense? In fact, we can do really in general. Then we could have if I have x equals some constant a times t, just to match the book, plus b, and if y is defined parametrically as ct plus d, c times t plus d, where a, b, c, and d are constants, and either a is not equal to 0 or b equals not, or c is not equal to 0. One or the other is not equal to 0. Then what this is going to be is this is going to be a set of parametric equations that form a line. The plane curve is a line. Okay, does that make sense? Because you can solve for one in terms of the other, as long as they're not. I mean, if they're both equal to a constant, then that's not really going to work because you can't sub in, right? Like I did on that one. Like I solved one of the equations for t and subbed it into the other equation. If a and c are both 0, you can't do that. So in this case, if they're not, then you have a line. Okay. Let's look at another example here, and change over here. If I have, I'm going to change up their second example just a little bit, and let's just say if we got x equals 3 cosine t and y equals 3 sine t. Okay, and we want to graph that parametrically. In this case, 0 is less than or equal to t is less than or equal to 2 pi. Actually, we don't have to have the equals on the 2 pi, but we're going to. So anyway, what happens here is we can eliminate the variable t. So in this case, t is like a theta, not time, right? It's like a theta if we want to think about it that way. But what we can do is we can square both of these and then add them together. So if I've got x squared, that's going to equal 9 cosine squared t. And if we have y squared, that's going to equal 9 sine squared t. And then we add those together, we're going to have x squared plus y squared equals 9 cosine squared t plus 9 sine squared t. So I can factor out a 9, and it's cosine squared t plus sine squared t. And of course, what's that equal? Sine squared plus cosine squared is 1, right? So this is 1. So anyway, we've got x squared plus y squared equals 9, which is 3 squared, right? This is basically a way that we can write it in terms of just x and y and eliminate the variable t. And of course, this is just the graph of this is going to be a circle with radius 3, correct? So over 3, up 3, left 3, down 3, centered at the origin. So that's a parametric equation, system of parametric equations that the plane curve is a circle centered at the origin with radius 3. Okay, but obviously, what did you do back in the good old days? You were just doing x squared plus y squared equals r squared, right? Which is not a function, is it? That's not a function, but is x equals 3 cosine t, is that a function? Yep. Is y equals 3 sine t a function? Yep, it is. Okay. Now I'm going to give you a little prelude because we've got the circles there. The parametric equation is a circle, and obviously it would keep going around it. Like if t continued, if we didn't stop it at 2 pi, it's just going to keep going around and around and around, right? So it's like the guy in the roundhouse that really had to go to the bathroom. He ended up dying because he couldn't find a corner to pee in. I don't know if you heard of that guy, but. Anyway, just remember I'm volunteering my time right now. All right. So jokes are free.
You can get a $10 gift.
I might not be allowed back in the building. They might take my key away. All right. I do kind of like this other one that they do, so I want to go through the example on page 779. But we have cosh and sinh. So we got x equals cosh t and y equals sinh t. All right, and so what's cosh by definition? That's so cosh x is x plus e to the minus x, isn't it?
Yep.
So it's e to the t plus e to the minus t all over 2, and y is going to equal e to the t minus e to the minus t all over 2, if you remember the definition of cosine, right? So I know, like Tim, I thought you said co is a minus. Yeah, that's when you take a derivative, right? Derivative of cosh is sinh, derivative of sinh is cosh. So there's no minus on those either. But anyway, so it works out kind of nice. But we can do something similar tactics. Can we rewrite this without the t's? Sure, we can square them both, and then you're going to get cosh squared and sinh squared, but what's the identity? Do you remember? Cosh squared minus sinh squared is 1. Do you remember that? Yeah, so if I square them both, I'm going to have x squared minus y squared is cosh squared t minus sinh squared t, and this equals 1, okay, because that was our identity in cosh and sinh back in chapter 5, I believe, okay. Anyway, so we got x squared minus y squared equals 1 is our, kind of hiding the variable t there. And so if I was going to graph this, anybody remember what that looks like? Y squared equals, I don't know, it's a hyperbola. So if you don't know, look in the book. So basically it graphs like this, right? Which that's over 1. Now, the thing is, it actually graphs on both sides of the axis, right? It's a mirror image like that. But they have so at -1. The left side, let's talk about this. So the reality is it's not x squared minus y squared equals 1. If it was, both of those would be darkened in as a hyperbola. But what's the reality? Can we be the left side? And to do that, we can just look at the x. So the left side would be negative x's, correct? Can x ever be negative in reality? In this case, can cosh ever be negative? No, because e to the t is greater than or equal to 0, and e to the minus t is greater than or equal to 0. Right? So you're adding two numbers that are greater than or equal to 0, which positive plus positive is positive, but they can't equal 0, by the way, sorry. E to the t can't ever equal 0, right? Or e to the minus t. It's always on or above the x-axis. So anyway, positive plus positive is positive, divided by 2 is positive, so x has to be greater than 0 based on this parametric representation. So that's why we're not including the left side, and the curve is the parametric plane curve. The plane curve C is only the right half of this. Does that make sense? That's why I wanted to cover that, because of how we're defining x. Okay, so once again, if this was just algebra, 2-dimension, we had x squared minus y squared equals 1. We have both sides of the hyperbola, but we don't here. Okay, so a couple other things. Just biggest thing is I want to give you a feel for it. But if we have, so here's a result. If we have a plane curve C, so if a plane curve C, so they call it capital C, is defined by y equals some function of x, which means basically like you graphed it before, like y equals x squared, y equals x cubed. Those are all plane curves that would fit this, right? The base graphs are all plane curves that are defined by y equals f of x, aren't they? Then what we can say, I need one more thing though. I need where f is continuous. So if f is continuous, that means what? We can draw it without lifting our pen, left to right, correct? Or on the interval, whatever interval you're looking at. So where f is continuous, then the parametric equations representing c. So parametric equations for c, for the graph, would be, so may be obtained by letting x equals t. So x would equal t, and if x is t, then y would equal, instead of f of x, y equals f of t. Okay, so if we have our continuous functions, y equals f of x, in a plane curve, we could also define them parametrically by just letting x equal t and y equals f of t. So that's kind of a duh thing, right? But what's nice about this, so they give a pretty simple example, all right? And you might say, well, what's the difference, right? But what if we got, like, if we have y equals x squared, how would you define that parametrically? Well, that's continuous, right? I mean, we can draw the graph. It's a parabola sitting on the origin, right? So it is continuous. So we can say, hey, if we define it parametrically and we want to rewrite it, we can let x equal t, and then y equals what? Whoa. And y equals f of t, which is t squared, right? That would work. That graphs to the same exact thing. So in this case, this becomes, t and then f of t, or y up here, tf of t. So y in this case would be f of t. So that's exactly the same, right? All you're doing is changing the variable, right? Aren't you? You're just changing the variable. So like instead of x, we call it t. So instead of the x-axis, we call it the t-axis. And you're like, this is stupid because anybody can do that. Why didn't we call it z? Right? Well, here's why, because z is 3 dimensions. We'll do that more in Calc 3. But because we could also have something, we could also define it like this. We could also let x equal t cubed and y equals t to the 6th. So if I did that, I'm going to have the exact same graph. Because t cubed quantity squared, the amen rule, right, is t to the 6th. So that's the exact same graph. But what can't it be? I'm going to use red. Red is bad, right? So I'm going to put but. If x equals t squared and y equals, what would y equal? T to the 4th, because t squared squared is t to the 4th, right? Are you going to have that same equation, same plane curve? The answer is no. There's a problem here. Why not? What do I actually have if I define it parametrically this way? I don't have the y equals x squared graph. What do I have? Think back to that hyperbola. What do you know about x in this case? It's never negative. So this x equals t squared would actually be greater than or equal to 0. So what would my plane curve look like if I defined it parametrically this way? It would just be the right half. Make sense? So we got to be careful on that. Also, if I had x equals t to the 4th and y equals t to the 8th, I would have just the right half. So we got to be a little bit careful how we do it, right? But do you see it's not just, you know, when you just replace the x with a t, like if I have a continuous function, replacing x with a t and y with the f of t, you know, that makes sense for the y equals f of x if f is continuous, but we have other ways that we can do it. To define it parametrically that work, we also have other ways that we got to be careful on because it's going to restrict your domains potentially. Okay? Don't worry, we still got time. We got 5 minutes, or your next one's free.
Trying to look up the little time thing at the bottom. Does that say when?
What time does it say? I have no idea. 11:20? It says 11:20, but that's not right, is it?
I was like confused.
Well, this computer sucks. Sorry, I'm not supposed to say that word. Apparently. Is that in the Bible?
Direct quote from Jesus.
All right. Now, I do want to talk about a couple other things. We have different types of curves. Okay. So we need some definitions, and then I'm going to try and like lead you into some easy odds, hopefully, things like that. But anyway, we want to talk about a smooth curve. But what do you think smooth? What would you consider smooth?
No sharp points.
No sharp points. Good. No rips, tears, jumps, sharp points, jagged edges, things like that. So that'd be smooth, baby. All right. Anyway, so we're going to define that. So plane curve C, I'm not writing out. This is on top of page 781, just so you know. But C defined by x equals f of t and y equals g of t. That gives a plane curve C is smooth. So it's a smooth operator. Smooth on the closed interval. So smooth. That's horrible. How can you even read that? Smooth on the closed interval a to b. Closed interval a to b. So t is an element a to b, right? So this means a is less than or equal to t is less than or equal to b. So t is in there. But anyway, smooth if f prime and g prime are continuous. So the derivatives of f and g. So f prime and g prime are continuous on the closed interval a to b. So if the derivatives are continuous on that closed interval and we don't have both of them equaling 0 at every point in the open interval. So anyway, so not both 0 on the open interval. A to B. All right, and just real quick is to finish up here. But so we have smooth curves can look like this, right? And maybe we're going left to right here. So there's a smooth curve, right? So no sharp points, so that makes sense. We also have closed. So we have closed curves if the start point and end point are the same. That'd be a closed curve, okay? And anyway, so like in this case, if I'm going counterclockwise and the start point and the end point are the same, that'd be a closed curve, okay? If I have a curve like this, I'm just going to draw some pictures. Here's a start point. Let's say I'm going this way and then this way. That's not closed, is it? It's not closed. And then anyway, go from there. And then simple, it doesn't like have any points in common. So the one in the last one I drew is not simple either. But I'll do more of this stuff tomorrow. So I'll just try and give you odds over some simpler parametric curves. Okay.